They say, okay, so today we're gonna go with rotational dynamics. And before that, you need to know a few topics that are must to know. First of all, you need to know what are the things in rotational dynamics that used to be in the normal dynamics, that is linear dynamics. So in linear dynamics and in rotational dynamics, we basically study the motion of items that take part. So first of all, it's linear motion. Imagine that there is a object A that goes to like from here and it reaches the point B. Object a point from object object An object from point A reaches to point B while traveling the linear route. Similarly, we have a rotational route and an object is right here, an object is in point A, that object reaches to point like B right here in a circular path. So to study the motion, there are different terminologies. For linear, it's simple, I don't have to discuss it. For rotational, it is like this. This is the radius of this circle that it is taking part. This is the displacement. This is the displacement, but in rotational dynamics, the displacement is measured in angle. So the theta is denoted by displacement. Similarly, other terms such as acceleration is given by alpha. Let me just write down here, okay? U is omega naught, initial velocity. V is omega, final velocity. Acceleration is alpha. Displacement is theta. And I think that much should do it. This is the fundamentals. Now we have the equation of motion, the fundamental equation of motion, as equal to ut plus half at squared. This in rotational dynamics can be written as theta will be equal to omega naught t plus 1 by 2 alpha t square. Another fundamental equation of motion is v equal to u plus at, which in rotational dynamics is given as v is omega equal to omega naught plus alpha t. Similarly, another equation, so you can do this, I don't have to say, I think, okay, yeah, these are the three basic rules. Yeah, and now we are moving to the derivation portion and the actual thing that comes in exam. And yeah, we also need to remember if the relation between velocity, radius and angular velocity. It is pretty simple, you must have guessed already. Omega will be equal to velocity by radius. Get it? Or you can simply say v equal to r omega and alpha equal to a equal to alpha r, like that. You need to remember these two key ideas. You will just remember it yourself even if you don't want to while doing numericals. So let's move on from this. Okay, now we're moving on towards the another section, moment of inertia. Okay, so what is moment of inertia? Moment of inertia is basically friction. Yep, it is completely logicless argument that moment of inertia is friction, but you can remember it that way. In linear motion, the equivalent of moment of inertia is friction, but mathematically it does not hold good. So you can define moment of inertia as the inability of a body to change the state of its rest or motion. Let me write down for you all. Moment of inertia, right? Moment of inertia can be defined as the inability of a body to change its state of rest or uniform rotational motion by itself or without the application of external forces is called moment of inertia. You can read it once. Moment of inertia can be defined as the inability of a body to change its state of rest or motion or uniform rotational motion. You must write this, by the way. Uniform rotational motion, if it comes in exam. By itself is called moment of inertia. It is mathematically given as I is equal to mr squared, and that's all you need to remember. You get it? You get it, right? I is equal to mr squared. That's all you need to know from this right here. Now we are now moving on to radius of gyration. And before that, factors upon which moment of inertia depend upon. You must know this. This is a very important short question in your NEB board exam. So the first factor is mass, obviously, because it is mr squared. So, and the second factor, you can basically write the radius, but that is a bit too not good. So you can basically write distribution of mass. For example, this is a random body and this is the axis, then the mass right here and mass right here. The radius is different. So even for same mass of these two particles, the moment of inertia experienced by them is different because of their radius. So the distribution of their masses changes the inertia. And similarly, the third factor is the axis of rotation. If this changes, if this thing changes, of course the moment of inertia also changes. Okay, now we're going to radius of gyration. Let's go to radius of gyration. So in radius of gyration, what you need to do, remember, is it is the perpendicular distance from the axis of rotation to a point at which the whole mass of the body is supposed to be concentrated, such that the moment of inertia remains the same. Remember this. This is also not that important, but somewhat important. So remember this. It is the perpendicular distance. It is the perpendicular. It is the perpendicular distance from the axis of rotation to a point at which the whole mass of the body is supposed to be concentrated, such that the moment of inertia of the body about its center remains same. That's it, right? This is the definition of radius of gyration. and that is all you need. Now we're going on to our first derivation, which is very easy and very important at the same time. This is the top 10 derivations from this chapter. This falls under the top 10 derivations from this chapter. So you need to focus, and this is like most likely in your examination. All right, then let me zoom out a little bit. Hope it's visible. I think it is. Okay, let me see up to which point. Okay, so let's start. The derivation is moment of inertia of a thin uniform rod rotating about an axis passing perpendicular to it and through its center. Just like that. Alright. For that you need a figure to make, and the figure is like this is a thin uniform rod with the axis being this. Let it be y o y prime, and this is a rod AB. Very simple, and it is rotating with a velocity of omega. Everything fair right now? Yup. The length of the rod, let's assume, is L from all the way up to here. This is L. Then we need to find the moment of inertia, total moment of inertia of this rod. Okay, so then first what we need to do, we need to write some language. Let's just try to consider a long, thin, uniform rod rotating about an axis about an axis the axis is y o y prime, passing through its center. Just like that. Then what we'd come up with is we need to also declare a small portion, because we're gonna of course integrate. So let's declare a small portion of the rod. Let it be a part here. You can do it anywhere. Let it be dx, and let it be at a distance of x from the origin. And to integrate, we need to assume this is minus L by 2 and this is L by 2, so that what happens is minus L by 2. Okay, let's do it later. Okay. Yep. Good till now, right? All good? Okay. So now passing through its center. Okay. Let dx be a segment of the rod at a distance of x meters, or you can just write units, from the axis. Then the mass per unit length of the rod is mass per unit length is mass by length. Simple as that. Yep. Then what we know is the mass of the segment. Dx will be equal to m by L dx. Okay, how did this happen, right? We use simple unitary method. How? The whole body, the mass of this thing is m. We know that, right? Then for like 1 unit length, for 1 unit length, the mass of 1 unit length is anything like 1 meter, one anything is m by L. Then for a dx, which is this much of length, this much, it is simply m by L into dx. That's it. That's how it works. Remember this. Now we move on to the next page, where we're gonna write mass of the segment, right? So now the moment of inertia, we now have the mass and we also have the radius, that is basically x. As you can see, the radius is basically x, just right here. So we just need to find the moment of inertia for that small part. We know that the moment of inertia of the segment is, let it be di, is equal to d mass is dm into the radius is r square, that is x squared, and we know that dm mass is m by L times dx times x square. If we do this equation 1, the total moment of inertia of the rod can be determined by simply integrating the equation 1 from negative L by 2 to positive L by 2. Okay, so now let me explain why are we choosing to do from negative L by 2 to positive L by 2. Okay, this is a graph, correct? And here is 1. This is the point of 1. You get me, right? Or you can just assume that this is the total length of the rod. Let it be L, point L. So if you make up in your mind, you can basically imagine a rod like this. Is it visible though? Okay, just right there. Yeah, you can imagine a rod being like this, right? The total length of the rod is like this. This is L, the point is L. If you pick this up and shift it such that its center, this is its center, for instance, if you shift it and make another graph so that its center lies in the origin, look at this. This is the origin. This, if you shift it, it will be something like this. This and this will be L by 2, this will be minus L by 2. You get it? And now we are not doing this one. Our question says the rod, its center is in the axis, so we're using this one. There is a derivation for this one as well. In this, after this, I'm not going to do that. It's the same thing, just to integrate from different, that is from 0 to L. But now since the center is in the axis, we're using this method. If there's any confusion, you can simply ask me. Okay, now we're moving to the derivation continuation. Okay. So you can, if you integrate it, it simply becomes I, the right hand side, left hand side becomes I, and the right hand side becomes minus L by 2 to L by 2 m by L dx x squared. We know that the mass by length is a constant quantity, so we can simply write this outside the integration, which gives us minus L by 2 x squared dx. Now this is one of the simplest integration of grade 12, so you can simply write this as x cubed by 3 and put the limits just like that. Now for this, what we need to do is replace the value of x by L by 2 and L by 2. So you basically do L by 2 cube by 3 minus L by 2 cube by 3. That's how we do it. And this will be m by L. This will be 3 to 8 by 3. Wait a minute. 8 by 3 plus. Okay, let me do it. L cube by 8 threes. What is 8 threes? Okay, it's 24, right? Yeah. So it will be 12 right there, yeah. Okay, yeah. It will be L cube plus L cube by 24. This is how it will happen. And this will be m by L, and this will be 2L cube, so you can cut 1 L and 1 2 to get 12. So this will be m by L L cube by 12. You can cut this, and this will be ml squared by 12. This is what you need. Now you can just simply write, therefore the required expression is ml squared by 12, and that's it. Your derivation ends right here. And if you want to find the value of k, that is the radius of gyration, then what you can do, let me check. Okay, what you can do is there's a relation that is k. We know that k is everything except the mass. Radius of gyration, you can see from definition, we know that I is equal to mk squared. So I is basically, k is basically everything except n, except for m. So it is k is equal to k square is equal to L square by 12. So this will give k will be equal to L by 12 under root. This is also done. So that much was it. Now there is another derivation for moment of inertia of thin uniform rod rotating passing through its one end. It's everything same as earlier. You just integrate it from 0 to L, and the answer you will be getting will be ml square by 3, and I'm not going to do that. So yeah, in exam this might happen like in one set it gives from center, and the other set it gives from the one end. So yeah, now we're going to rotational kinetic energy and torque of the bodies, and then we're going to do everything else in the next part of this video. So stay tuned for the next part. Till then, chill out, bro.